Okay, so for the ICMP lab, the first thing we're going to do is set up something similar to what I have displayed on the screen, my rudimentary network diagram. Um, I made this using the awesome tool called a pencil and a piece of paper. So what we have one rack represented here. There's a router, two routers, two switches. The line in between kind of delineates our two different LANs, our two different networks connected with serial. We configured inter VLAN routing. We have one Windows PC and one Linux PC, or in this case, I actually have a Linux PC that is running in a virtual machine on a Windows PC. But anyway, I have 192.168.10.2 for Windows, 192.168.20.2 for Linux on my side. The other side has 30.2 and 40.2 respectively. So if we look at the lab sheet for this week's lab, which I guess I could probably open, which might make this a little easier. We look at the lab sheet for this week's lab. If we look at the lab sheet for this week's lab, if we look at the lab sheet for this week's lab, there we go. We're going to be looking at ICMP traffic. So ICMP is a helper protocol that goes along with IP. If you recall from our studies with IP, IP is connectionless and unreliable. So we use ICMP to try to build in some help to our connectionless and unreliable protocol. So ICMP will respond to us if there are some issues that ICMP is familiar with and that it can help us out in solving. So what we're going to do is we're going to generate some traffic on our certain machines given the commands I gave you, and that's going to cause some error conditions to exist, and then we're going to analyze the traffic that comes back in Wireshark. So the first thing it says is to ping the other side and look at an echo request and an echo reply. So let's go ahead and start Wireshark. Go ahead and start Wireshark. Interface, start. And we'll put an ICMP filter on for now to see only what we want to see. And I apparently am still pinging somewhere. Oh, yep, I was pinging down here from my Mac to test it out. So I was pinging down here. So let's go ahead and look at one of these. I said look at an echo request and an echo reply. So here's an echo request. Right, and what did I want us to look at in the echo request and echo reply? What is the type? What is the code? In echo request, we need to go down to the ICMP message protocol section. An echo request is a type 8 code 0. If you look at the ICMP, the IP, TCP IP cheat sheet I gave you, you'll see the types and codes all listed, and that helps tell you what each different particular ICMP message is. So in this case, we have type 8 code 0. And if we look at an echo reply, we also see that it is a type 0 code 0. So that's that. And then down here, we have the data that gets sent along with the ping. In this case, it was 48 bytes. As you recall from some previous labs, we sent different data sizes. So you can change that, and it will send more data. So that's that. So then let's look at the lab sheet again. The next thing we're going to do is I've given some commands here that we are going to use to cause some error conditions to exist and to force some ICMP replies from other devices in the network or other hosts. So if you look at this, I've already set my MTU on my serial interface to 700 because we're going to need that in a little while. And then it says substitute the IP address of one of your partner's hosts for x.x and the IP address of your other machine for y.y. So let's go back to my picture, if I can find it. If it says x.x, you should ping one of these guys. If it says y.y, you should ping your other machine, your Linux machine. And these first list of commands we're going to be doing from Windows. So from our Windows machine, if it says x.x, I'm going to substitute 30.2 or 40.2. If it says y.y, I'm going to substitute my 20.2. So let's go ahead and do this first command. Well, actually, I'm going to restart Wireshark first. Capture, restart. So there we go, ICMP. Let's go find my window, not that window, command prompt. There we go. Here's my command prompt. The command I said I wanted us to run is trace RT 192.168x.x. So something on the other side. So I'm going to do trace RT 192.168.30.2. That'd be my other Windows machine. I'm getting stuff back, hopefully. Just wait and see what happens. So 10.1, 50.2, and then the final host of 30.2. So if we look at my diagram again, right, what traceroute does is it sends, well, let's look at what traceroute does in Wireshark first. That's not what I wanted. Trying to find my Wireshark window. There it is. All right, let's look at what traceroute does. Traceroute, we can ignore these. These are messages that were caused by something else we're not doing. So traceroute sends pings with low IP time to live fields. Wait, that's the wrong ping. Low IP time to live fields. So if we look at this first one I sent, the time to live was 1. So what's going to happen is the router is going to decrement that to 0 and send back this time to live exceeded message. If we go a little farther down, this one, the time to live is set to 2. So the first router will knock that down to 1 and pass it on. The second router will knock that down to 0 and send a time to live exceeded message. Right? We go down a little farther. This one is set to 3. The router is going to knock that down to 2. The first router is going to knock it down to 2. The second router is going to knock it down to 1. And the third router, or host in this case, is going to send knock it down to 0 and send a time to live exceeded message. So what happened was, when it was 1, this router killed it and sent it back. When it was 2, this router killed it and sent it back. And when it was 3, the final destination host killed it and sent it back. So that was what we were looking for. So let's go look at the lab sheet. It says, what traffic did this command generate? Well, you need to somehow summarize those things I just said. Decrementing time to live numbers, frame number. Here you should identify some of the frames from that. So the first frame number would be 411. The second one would be 471. And the third one would be 523. Do we need to put every frame? Because each time we did it, it sent 3 packets with that time to live in case some of them got lost. So do we need to put all those? No, just one for each time to live, so you need 3. And then the other thing I wanted was ICMP reply. That was time to live exceeded in transit, I think it said. Yeah, time to live exceeded in transit. Scroll over a little bit. In transit. And then it asks for the type and the code, so we'll open one of these guys up. Find the type and the code. Type 11 code 0. And then I also wanted the frame numbers for some of these replies. So you should find the frames that matched up with the frames you gave me. So if the first frame you told me was 411, then 412 would be a reply. If you told me 471, 472 would be a reply. And if you told me 523, then 563 maybe. No, that's not right. Yeah, I don't know. Find the reply for that. All right, so that was the first one. Well, I think there's something else I want to talk about this. And then reason for response. Lots of people will just put the same thing as what the name of the reply was. That's not really what I'm looking for. What I'm looking for in this case is reason for the response. The router decremented the time to live to 0 and sent the ICMP error message, something like that. One other thing I want to look at, if you notice there's a lot of different ICMP error messages showing up. These destination and reachable messages are kind of clouding things, but that's not what we're trying to look at right now. If you want to help find what the error message is related to, if you open the frame that you're looking at, if you go down to the bottom of the ICMP section, so here's the ICMP section, it says the type and the code, and then the next thing in the packet is the first part of the datagram that caused the problem. So if we look at this, this is an IP packet from 10.2, destination of 30.2, with a time to live set to 1. So this was the original packet that caused the problem. And that's helpful lots of times in figuring out what caused the problem, where the error message came from. Another thing, lots of times you might expect that, oh, well, okay, well, I'm always going to get reports of these error messages because the machine's going to tell me when I do it that there's going to be a problem. So let's go on to the next one because this is a good demonstration of that. So let me restart this. It might be helpful for you to restart the capture every time and save it. So I'm going to want you to submit all these capture files. So you can keep one long one running forever, but you're going to need to be very careful about noting the frame numbers that you are using because I'm going to look for those. Or you can restart the packet capture every time. You can do stop, and then you can save it. You can export those specified packets. You can select the ones I want to see somehow. I don't know if you can select multiples. Yeah, I don't know. Somehow you can select the packets to see what I want to see. But then you'll restart it again if you want and capture more traffic. So I don't want to save it. All right, so now I'll start it again. I'm going to go find my command prompt. Find my command prompt. And this time I'm going to do the next command on my sheet, which was ping-f-l800, an IP address on the other side. So we should remember what this command does. -f says don't fragment. -l says send an 800 byte ping, and we set the MTU to 700. So what should happen there? You're right. It should not make it. -l800. We're basically saying, hey, send this big packet, but don't fragment it, even though it needs to be fragmented. So in this case, our command prompt actually tells us what the error message was, which is helpful, but it's not always going to be the case. So let's look at what we have in Wireshark. In this case, we send an echo request. In this case, we send an echo request in frame 472. The reply comes back in frame 474, right? Destination unreachable, fragmentation needed. So let's look. Our type is 3.4, type 3 code 4. So let's go look at our lab sheet. Our lab sheet. What traffic did this command generate? It generated a 800 byte ping with a don't fragment bit set in the proper frame number. ICMP reply, fragmentation needed but DF bit set. The frame number for that, in this case, you know, the first one was 472, then 474. Type 3 code 4. Type 3 code 4. Reason for response, packet needed fragmented, but the don't fragment bit was set. So that's that. The next one, ping-k. Ping-k. If we run ping with a / mark, it tells us some of the things. Ping-k does strict source routing. With strict source routing, you specify which routers the packet is permitted to go through. So this is a way you can say my packets can only go through these IPs. It's not really useful for much of anything as far as I know. Testing mostly, maybe. That's what we're using it for. So in this case, we're going to do ping-k, the IP of your gateway. So if we look at my picture, where's my picture? If we look at my picture, this is my PC, so my gateway is 10.1. So the first hop is going to be, the first number is going to be 10.1. And then the second thing is going to be the IP of your neighbor's serial interface. So that's going to be 50.2. And then the third thing is one of your neighbor's hosts. So let's go try that. So ping-k, my gateway, dot 192.168.10.1, my neighbor's serial interface, 50.2, and then the last thing we want to put is my other machine, right? So basically what we're saying is, hey, I want you to ping this machine and the packet must go through this interface, right? So that's going to fail and give us an error message, which is what we want. So let's put 168.20.2, which is my other machine. And there we go. I get my error message, invalid source route specified. I guess I stopped my capture file. Oh, yep, stop my capture file. Let me restart it. Do it again. So if we look at our traffic, here we have, go ahead and stop this. Here we have the frame I sent. If we want to look at the source route, that is an IP option. So we can go to the Internet Protocol, go down here to our options, and we have a strict source route option that tells which hops it can go through, right? So that's the frame that caused the problem. And the response is destination unreachable source route failed, type 3, code 5. So if we look at the lab sheet, we have ping-k, IP of the gateway, blah, blah, blah. What traffic did this command generate? Generated a strict source route, a packet with strict source route IP options. Get the frame number. ICMP replied, strict source route failed. Source route failed. Right, type was 3, code 5. Reason for response, we tried to force it to do something that's not possible. We specified an interface that this packet, we specified a source route that was not possible. The next thing we're going to do is ping an IP address that does not exist in our network. You might get 2 different responses depending on what you have set up. I set up default static routes, so I'm going to get, what the heck's that? I don't want you to do that. I set up default static routes, so I'm probably going to get time to live exceeded eventually, I think. If you set up RIP and didn't set a default route, you'll probably get some sort of destination unreachable message that's not to do with time to live exceeded. So let's restart this. Capture, start. You're going to be saving all these, so make sure you save things. So let's ping that address, 92.168.100.100, and wait a while. So TTL expired in transit, so that's what I was expecting to get in that case. So what happened? Well, let's look at the traffic. Here I sent an echo request. Here I got a time to live exceeded message from the router. Again, this is going to be the same thing we saw earlier with the trace route. Type 11, code 0. And let's go find my drawing. So what happened was, that's not my drawing. So what happened? That's not my drawing either. There it is. So what happened was the ping got to this router, and it checked the routing table, and the router used the default route to send it to this router, who checked its routing table and used the default route to send it back to this router. So that packet just bounced back and forth between routers until the time to live expired and it got killed. So that's a good example of why the time to live header field is needed. If there was no time to live or no mechanism to kill packets, that thing would just bounce around forever. Time to live expired and it killed the packet. So that was it for the things we're going to do from the Windows side. I'm going to do another podcast for the things we're going to do from the Linux side, and then we'll finish this up.